The biggest problem with renewable energy isn't generating it, but storing it. Right now, we can generate huge amounts of clean electricity from wind and solar, sometimes even more than we need. But here's the catch. When the wind stops and the sun disappears, where does that energy come from? Batteries help, but only for a few hours. Pumped hydro works, but only in places with the right geography. So what fills the gap? There is a gap, and it's a big one. And one technology might fill that gap using nothing more than air. It sounds simple, and at its core, it really is. Compressed air energy storage, or CAES, is exactly what it sounds like. You take electricity when it's cheap or abundant, use it to compress air, store that air, and later release it to generate electricity again.
So you use the electricity to make the compression work, and it will compress air and send it to air tank. The trick of compressed energy storage is that you have to make the system reversible in some way. So you have to be able to take the air from the tank, put it in some kind of turbine or expander, and as it expands, it will make the compressor act as a generator and send electricity back to the grid.
It's basically like a giant mechanical battery. Instead of storing energy chemically, it stores it as pressure inside a tank. Just as a battery holds energy in chemicals, CAES holds it in compressed air. But here's where things get interesting.
Compressed air energy storage is not a single technology, it's really a suite of technologies. So it's a bit like saying, lumping all batteries together.
Which means not all CAES systems are created equal. CAES isn't a new idea, so why are we talking about it now? CAES has actually been around for decades. But for most of that time, it struggled to compete. So what changed? Renewables. Wind and solar are now flooding the grid with cheap electricity, but not always when we need it. And that's creating a new problem: long-duration energy storage.
I would say, compressed energy storage is not dedicated for really short-term storage, like few minutes, 1 or 2 hours. I think batteries will be more competitive on this one. Compressed energy storage starts to be competitive, and even more competitive as you increase the duration of storage. It's more complicated to do gigawatt installation plants. It takes quite a long time to develop. But for megawatt system, what we call long duration energy storage, 5 hours, 10 hours, stuff like that, up until 30, maybe 40 hours. This is the range where compressed energy storage is really, really competitive and has an advantage over the other ones.
In other words, CAES isn't trying to replace batteries. It's trying to do what batteries can't do economically. But if CAES is that promising, why isn't it everywhere? Because compressed air has a dirty secret. When you compress air, it heats up. When you expand it, it gets cold. Very cold.
When you take air, which is at room temperature, for instance, and you want it to expand, it will drop in temperature. It will freeze, and it will freeze all the water which is inside the air, and you will make ice. And it's a big issue when you want to get back energy if your whole system is frozen. So it was the main issue that all the technology now are trying to solve, is how to circumvent this issue.
And ice inside a power system is not ideal. But more importantly, that temperature swing wastes energy, and that's the real killer.
The big challenge in compressed air energy storage can be summarized by 2 words, and that's heat management.
Lose the heat, and you lose efficiency. And if efficiency drops too far, the economics collapse.
Efficiency is the problem. Companies trying to develop compressed air energy storage don't manage to hit the metrics that they would require to sort of secure the next round of funding. They get so far. A lot of these companies have very interesting innovations, but they tend to have one innovation in a system that probably needs a handful of innovations in order to make it viable.
So how do you fix a system that wastes its own energy? The answer? Control the temperature. Instead of letting air heat up and cool down wildly, you try to keep it at a steady temperature. which is what engineers call isothermal compression.
You can increase a lot the temperature in the system, so you can go from 10 degrees to 300, sometimes more than 1,000 degrees if you try to compress the air at high pressure. And our system, the idea is to maintain constant the temperature during the whole process.
That means less wasted energy, simpler storage, and better overall efficiency. But this isn't easy. You need advanced heat exchangers, clever engineering, and systems designed to handle high pressures. But where do you actually keep all this compressed air? There are two main approaches. Firstly, storing air deep underground, in natural formations like salt caverns.
And salt caverns are amazing technology. So once you get to 500, 600,000 meters cubed of cavern, the cost per unit of energy stored in that system is very low.
These systems are huge and built for the grid, and they're incredibly cost-effective if the right geology is available. And then there are above-ground systems. Smaller, modular, flexible, but more expensive per unit of energy. Think of it this way. Underground storage is like a massive water reservoir, ideal for holding large amounts of energy over long periods. Above-ground systems are more like tanks that can be moved easily, useful for flexible and rapid deployment, but on a smaller scale. Different tools for different jobs. Which brings us to the economics. Why hasn't this scaled up everywhere? Because CAES systems are expensive upfront. Very expensive.
Why are we not seeing more of this is just that it's high capital cost.
But here's the twist. CAES has a unique advantage.
In a market where batteries are making very big advances, the attraction of compressed air energy storage really is that you can decouple the cost of power from the cost of energy. There are a number of other small things, but the size of your pressurized air store and your heat storage scale broadly independently from the size of your turbo expander or however you're doing the expansion. And so that allows you to make a system which can discharge at full power for, X amount of hours, where X is probably going to be some number greater than 8, and in my opinion might be greater than 12 or 24 before it finds a niche.
This means the power system of turbines and compressors is one cost, and the storage volume of caverns and tanks is another. And that's a big deal, because it means you can scale storage duration cheaply, something batteries struggle with. That begs the question, where is CAES a good fit? Not everywhere, and that's important.
It's never going to beat batteries on efficiency. Like that, I think for me that's very true. So it has to go hand in hand in an area where there's a lot of renewables that are fairly cheaply available. Let's say I'm in a wind-dominated system and I'm expecting that in the winter I'm going to have 3 or 4 days, no sun, no wind, and I want power output generated locally. That's the kind of area where you might be looking at one of these systems, having a very strong market opportunity.
So CAES needs the right conditions. Think wind-heavy regions, remote grids, industrial clusters, areas needing 24 to 72-hour storage.
There is a niche for a technology which can store, say, 24 to 72 hours of storage in wind-dominated systems like the one that we will end up in the UK in winter. And doing this at large scale, I think, is something that we will be wanting to do in future. And if we can make it cheap, cost-effective enough, I think technologies like compressed air energy storage are leading, in my opinion, in that kind of area. Because the general trend is that as you go longer duration, your system gets less efficient, right? So on the longer duration, we're maybe looking at synthetic fuels, hydrogen. The round-trip efficiency on those, I'm expecting, is going to be less than 50%. Whereas for compressed air, we might be in the 60 to 70, and we have more ability to cycle, these are going to look like fast-acting gas plants. And then on the shorter duration than that, we're going to have batteries because they'll be cheap enough to cover, maybe anything up to 8 hours.
That's the sweet spot. Too long for batteries, too short for hydro or hydrogen. So, how does CAES stack up environmentally? Compared to batteries, CAES uses mostly steel, standard industrial materials, no rare earth metals. That can be a significant advantage.
We know that we do not have a lot of critical material on European soil, and our idea with our system is to make it work with only air, water, and a lot of steel. A lot of steel for all the parts, but not use any critical material in the system. Actually, the fact of going from prototype to industrial, part of this is to remove any exotic material in the system. So even stainless steel, you can have some interesting critical material in stainless steel. We are going into carbon steel, cast iron, this kind of stuff. And it's really important because if we want to achieve a good level of sovereignty on this technology, we cannot depend on something that can only be produced on the other side of the planet.
But it's not impact-free. Underground systems require geological intervention. Above-ground systems require large installations. But in terms of life cycle impact, CAES could have a much lower impact, especially when used at scale. So, is this the missing piece in energy storage?
Most of the market right now are trying to find the missing block between the batteries on one side and the pump hydro, really long, or even sometimes hydrogen, really long-term storage for interseasonal system. But when you want to store for a few weeks, maybe a few hours to a few weeks, you have a missing block right now in the energy storage technology chain, and I see it as the technology with the most potential to fit this missing block.
That gap between short-term batteries and long-term hydrogen or hydro storage, it is exactly where CAES lives. Compressed air energy storage isn't perfect. It's not the most efficient, it's not the simplest, and it's not the cheapest option yet. But it solves a problem that nothing else does quite as well. Long-duration storage, at scale, without rare materials. And in a world powered by renewables, that might be exactly what we need.